All right, so logarithms. All right, so first thing that I want you to remember is a logarithm
Yield to room 102.
is the same as an exponent. Okay, a logarithm is the same as an exponent. So they are very similar in the properties that they have. So when we talk about properties of logarithms, exponents are going to be kind of referred to here. So with this stuff, so the first thing that we want to talk about is kind of how a logarithm equation is laid out. And what you have is log and then some base. And then you have something that you're taking the log base of. So this might be a 2, this might be a 10, it might be any number here as the base. And then you have something that you're taking that log base of, and then it's equal to the exponent. Okay, so this reinforces the statement that a logarithm is the same thing as an exponent. So a logarithm is equal to an exponent. Okay, so logarithms are exponents. That's what they're equal to. Purpose in logarithms is to take really, really large numbers and make them more manageable, or really, really, really tiny numbers and make them more manageable. Is the idea is that if you can take the log of that really large number, it gets it into more of a normal number that we're used to dealing with, instead of, the you think about the national debt, whatever it is, in the trillions of dollars now. Yeah, a whole bunch of zeros at the end, but that's not really manageable in a normal sense. But if you take the log of it, then it becomes a more manageable number. And depending on what base you use, what that ends up being. All right, so the first thing that we want to do is take a logarithm and rewrite it as an exponential. Okay, so we're going to write the logarithm as an exponential. All right, so what that means is we're going to take a problem. We'll call it log base 2 of 8 is equal to 3. So we're just going to put some numbers in the place of that. And we're going to rewrite that as an exponential equation. And what it means by exponential is a problem that has exponents in it. That's what an exponential is, okay? So when we talk about things with exponents, we talk about the base and then the exponent and then what it's equal to. So when we think about logs and their relationship with bases and exponents, when I read this, it's log base 2 of 8 is equal to 3. What's the 3 according to this line up here? It's the exponent. When I read this, it was log base 2. What's the base? 2. So the base is 2, the exponent is 3. So when you rewrite that, it's 2 to the third power is equal to 8. Whatever the base is, that's the base of your exponential. Whatever the log is equal to, that's your exponent. Okay? What this is going to lead up to later on is tomorrow when we start doing equations, sometimes you can rewrite the equation that's a log equation as an exponential, and it makes it easier to solve. Sometimes you can rewrite an exponential equation as a logarithm, and it makes it easier to solve. So the idea is to manipulate the problem to make it easier to do, kind of like we've done throughout the semester. We would rearrange the problem to the right way to make it easier to work. All right. So let's look at another one and let you get the hang of this. This is not hard, and it doesn't take any kind of calculation. What's the base? What's the exponent? What's it equal to? Boom. What's 3 to the fourth power anyway? It's 81. 2 to the third power is 8. These are all true statements that we're dealing with here. Shouldn't. They may throw some variables in there. But still the idea is what's the base, what's the exponent, and what's it equal to? X. All just based on location of the parts for the log statement. All right. Where they start throwing a little bit of knowledge in here is when they have a problem like this, and they'll just write log of 1,000 equals 3. And they don't put anything down here. What that's called is a common log. Common logs are the logs that we're used to. And when they don't have something written there, the log that you're dealing with is a log base 10. The reason that's called a common log is we live in a base 10 number system.
Levi Abels, Rain Miller, Carson Plunk, Michael Preston, Kate Price, Carly Tate, Christopher Thompson, and Asia Wicks report to the library. Nicholas Maples and Keith McAllister. The first group to the cafeteria, and then Nicholas Maples and Keith McAllister to the library.
She needs to go. That's a hot tea. All right, so base 10, we live in a base 10 number system. You think about the place value stuff that we've done. You got the ones position, the tens position, the hundreds, thousands, 10,000s. That's all base 10 stuff. So log without anything written there is really log base 10. Okay, so remember that because they're not going to usually write that 10 there. It's just going to be log of 1,000 is equal to 3. But you've got to remember, hey, that's base 10. So this would actually be 10 to the third, which is 1,000. Yeah, so easy so far. All right, another common log is one that's used more often in science connotation with biology, and you talk about bacterial growth and things like that, and that's the natural log, LN. Natural log is what it stands for. Okay, and natural log is, if you look on your calculator, I'll show you another helpful thing here. Look down the left-hand side here. You've got a log button and then an LN button that's natural log. Those are common logs, so they have their own button. The rest of the logs that we have to find, we have to use, it's not got a button for it. There's another way to get it done. But LN, if you look in the blue above that, it's e to the x. So the base for natural log is base e. So natural log is actually log base e.
Is that why on the calculator it puts in an E?
Now the capital E and the lowercase e are
The
two.
lowercase E sometimes.
Yeah, that's the exponential number is what that is. So natural log is log base e. They're always going to write it ln, but in your brain, think ln means this. Okay, that's what you want to think. And then, so if we're going to rewrite that, it would be a base of e exponent of 5. Okay. So again, they're going to write it ln, but you know that that's log base e is what that stands for. Okay.
Is log and ln the only two ones?
That's the only two common logs. You could have any other base that, as long as it's a real number, you can have that base. But the common logs are log base 10 and log base e or natural log. Those are the common logs out of that. All right, so rewriting a logarithm as an exponential, the base is always there. It's equal to the exponent, and then so log base 5 of x equals y. It's 5 of the y equals x. That idea. Let's go the other direction. So let's rewrite it as a logarithm. So write the exponential as a log. 5 to the third is equal to 125. So when you look at that, what part of that is the base? The 5. So when we do our log, what log base are we going to do? Log base 5. What part is the exponent? 3, and that's what it's equal to. So the 3 goes on the other side of the equals. So the 125 has to go here. Six squared is equal to 36. We all know that's true. But let's rewrite it in logarithmic form. Log base 6 of 36 is equal to 2. It really is that easy, folks. Don't let the variables confuse you. Three to the x is equal to 30. 3, 30 equals x. Good job. It did only stay this easy. Yeah. To a fault. 10 to the 5th equals 100,000. It's true. Let's rewrite it in logarithmic form. So what kind of log are we taking? This log, it's really log base 10. We know that's, they don't write the 10 there. It's understood to be there. Of 100,000. I'm going to put that in parentheses. It's got some zeros in it. Is equal to 5. Parentheses are optional. I kind of like putting them in there. All right. What's the exponent on that e? What's the exponent on that e? 1. If it's not there, it's understood to be a 1. Okay, so what log are we using here? ln. Natural log 2.71. 1. Yeah, log base e and natural log are the same thing. Okay, well, you want to write it as ln, natural log. Okay. And this will come into play tomorrow. We start solving some equations and rewriting, being able to rewrite them as a exponential or a log can make the problem a lot easier. Okay, let's look at the next thing. We'll do an easy one first. Evaluate without a calculator. Why do we need to be able to do that? That's one reason. That's a good reason. That's coming up soon, so yeah, that's a good reason. Also, it helps us think in the right ways for when we go to solve some equations later on. We can think in this way, it's going to help us be able to rearrange a problem to make it easier to solve. So if we think this way, it'll help. All right, so the first one we want to do is a pretty easy one. Let's do log base 4 of 16. Okay, I want to kind of show you how I go about doing this, and some of you can look at it and think it real quick. But what I do is anytime they ask me to evaluate that, they don't have it as an equation. So I'm making it an equation, and I'll change it to equals x. Just make it equal to x or some variable, whatever your favorite variable is. Yeah. Can't use e. It has meaning. Yeah. Can't use e, can't use I. or O? Because O looks like a 0, right? I is the imaginary number thing. So E and I and O are no-nos for variables. So I'm using X. Now, if I rewrite that as an exponential, what would it be? All right, and then I can think, hey, 4 to what power gives me 16? 2. So that tells me that the log base 4 of 16 is equal to 2. Let's do another one, pretty easy one. The ones that they ask you to evaluate by hand without a calculator are never going to be really complex. You're not going to get decimal solutions out of it. It's always going to be nice, easy numbers or numbers that work out well. Okay. All right. So again, I'm going to set it equal to a variable. Use a y this time. 2 to the y is equal to 32. And maybe I don't know my base 2's very well. Maybe I just need to break down the 32, 8 times 4. And maybe that helps me. 1, 2, 3, 4, 5. So that's 2 to the y is equal to 2 to the 5th. So what's y got to equal? 5. So log base 2 of 32 is equal to 5 out of that. And that, if you don't know the number, think factor tree and break it apart. Okay. Some of you probably already knew 32 is 2 to the 5th, but if you didn't, you can break that apart. It's not like it fell down the drain or something. A very unfortunate place to put the drain. Log base 3 of 27. That's a good one. So again, you could set it equal to a variable, kind of help you think this out. So it's 3 to the x is equal to 27. And I know 27 is 9 times 3, 3 times 3. So that's 3 to the 3rd. So log base 3, 27 is equal to 3. So without a calculator, that's kind of the idea how you want to think your way through those. Okay. With a calculator is the next thing. So this is really the easier part. Evaluate with. So we know in life everything doesn't work out to be perfect numbers all the time. We tend to make them do that in math classes to learn concepts and ideas, but we know it doesn't always work out that way. And we might end up with a problem like this where we had log base 2 of 12 and we had to evaluate that. Okay. And so there's a couple of different ways to do it. I want to show you both ways because some of you may prefer one way or over the other. So log base 2 of 12, we know 2 to a power, 2 to the 3rd power is 8, 2 to the 4th power is what? What's 2 to the 4th power? 16. So 2 to some power equals 12 would be somewhere between 3 and 4, right? What we know, just in number sense wise. But we can get the exact value or a decimal approximation of that value using the log base tool on our calculator. All right, so log base on a calculator is found by hitting the math button and then press the up arrow, and it should be down toward the bottom there, log base. And it should come up like this for most of us. So to find that again, you're hitting math, and then it's down toward the bottom of the list, so I just press the up arrow to get there. And log base, and then you put the base in, so it's a base 2, press the right arrow key, and what you're taking the log of, and hit enter. And let's go 3 decimal places with that. So 3.585. So approximately 3.585. So log base lets you type it in exactly like it's written there. Okay. There's another thing called the change of base formula, which allows you to use common logs. And this is pretty commonplace before the scientific calculators had the log base function on them. They didn't always have that. That's kind of new for the last decade. They've had that. But most calculators, scientific, like those little scientifics that are over there, have a log button or a natural log button on them. They just don't have the log base. So you can actually do. You can actually do the log of a base 2 using common logs. So you can actually do log base 10 of 12 divided by log base 10 of 2 and get the same number. So if on my calculator, I just did log of 12, close the parentheses, divided by log of 2, exact same number. It even works with natural log. Same number. Okay, change of base allows you to use the common logs to do that. And I don't care which way you do it. It doesn't matter. I tend to do change of base just because that's what I've always done. That's the way I learned it. The log base is a great tool, and it's free on the calculator to use. But if you ever catch yourself somewhere needing to do a log, like at the grocery store or something, I'll never do that. But if you ever and you don't have a graphic calculator with you, your iPhone calculator will have that on there too. If you turn it sideways. I don't know about the Android stuff. That's beyond me. I don't do the Android things. So where it really comes in handy is on problems that are a little more difficult to estimate. So we could estimate that one would have an answer between 3 and 4. This one with a log base 1/3, that's a little bit more difficult to estimate because we don't think in fractions very well, right? But since we're estimating this with a calculator, I'm going to straight up, I'm just going to do it that way. On log base, I'm going to put in 1/3, 1 divided by 3, and then 28. Negative 3.033. It could be. It's not very common for that to happen, but it could be. One thing that will never be a negative number is what you're taking the log of. That's always going to be positive. We'll kind of talk about that a little bit tomorrow when we solve. Relates to the domain of logarithms. All right. Natural log of 6. That one's easier because you don't have to do anything but hit natural log of 6. You got a button on your calculator. It's natural log. It's right beside the 4. Type in a 6 and go 3 decimal places. So 1.792. And then kind of to reinforce what Emma and I were talking about there. If you have a negative that you're trying to take the log of, that's not possible. There's no way that I can raise 3 to a power and make it turn negative, no matter what the exponent is. Even if I use a negative exponent, 3 to the negative 1 power is what? Somebody answer. 1/3. Yeah, and 3 to the negative 2 would be 1/9. So it gets to be a smaller number, but it never changes signs, right? So no matter what I do to this 3 as the base, it's never going to turn into a negative number. Right? So we can't take the log of a negative number, no matter what base is right here. So it's just undefined. Okay, so anytime that comes up.
Are there ever gonna be like word problems, so we have to use the log?
Yeah, we'll get there.
Well, it's testing out, it's gonna.
You'll see that more in college algebra than you will in algebra, because we're trying to just catch a skill here. All right, let's look at properties of logs. A lot of examples today, but not hard stuff. So
We're gonna need another alphabet.
we will get past the Z today. We have to choose. We could use the Greek alphabet. I have a different way of doing it. Properties of logs. We have what's called the power property. And it's not so necessary that you know the name of the property as it is to know how it works. Okay. So the power property, what it says is you can take a log of whatever base, and then you have the thing you're taking the log of has an exponent on it. What the power property says is, oh, I can take that exponent off of the number that's or letters that are being taken the log of and put it down in front and make it a multiplication problem. Yeah, just put it in front of everything there. In front, it's n, instead of being log base b of n to the n, it's now n times log base b of m. The reason these properties are important is when we go to solve equations, multiplication is a lot easier to undo than an exponent, right? Because division is a lot easier to do than taking whatever root we needed, right? That's the idea of the power property, is that it can simplify things for us. Okay, the next one is called the product property. What operation do you think it entails? Multiplication.
Oh, wait.
Products.
Oh, God.
That's okay, it's early. You've been out for a few days. All right. So if we have a log of whatever base, doesn't matter what the base is, but we have two things that are multiplied together on the inside of that log. What's the rule for exponents when you multiply? Like if I said x squared times x to the third, you add them up. So remember that logarithms are exponents. So you can take this problem and split it apart from multiplication into addition. Log base b of m plus log base b of n. That's what the product property does. Multiplication turns into addition. And then we get the quotient. Yeah. And what's the rule for exponents when you divide? Subtract them. So if we had m divided by n, it would be log base b of m minus log base b of n. So the numerator is first minus whatever's in the denominator of that fraction. So what we're going to do next is take these properties, and the first thing we're going to do is what's called expanding a logarithm. So we're going to take a single log and split it apart into its individual pieces. Let's change it. All right. So taking a single logarithm and expanding it out into smaller pieces, individual pieces. And then we'll go the other direction. We'll take one that's expanded out and condense it into one. Okay. So the expanding really helps us learn the properties. The condensing or writing as a single log really is the skill that we're after at the end of this thing to help us solve equations. So let's look at doing a few of those things. Okay. So expand the log into a sum / difference. All right, so we'll start with an easy one. What letter are we on here? Okay. R. Good. I'm gonna use log base 3. It does not matter what base the log is to do these properties. They work for every base. Okay. So log base 3 of x to the 7th power. So this one is a prime candidate for the power property because you have a log of something with an exponent. So the power property says that I can bring that 7 to the front, and it ends up being log base 7 times the log base 3 of x. There's nothing else inside of the log, so that one's is as expanded as it can be. So we're done with that one. Really, really easy one to start with. Just using the power property out of that. Do log base 2 of 3x. Okay. What's going on between the 3 and the x? They're multiplying, so that can be turned into addition. So we're going to do log base 2 of 3 plus log base 2 of x. Nothing I can do to expand that any further, so that's the... Because there's not any exponents or any other operations going on inside of any of the other pieces of logs. We're going to get to some that there's more to do as we go there. Do another easy one here. Log of x divided by y. So got a fraction in there, so that's division. So that's going to turn into log base x minus log base 10 of y. And I know that's log base 10 because it's a common log. There's nothing that written as the base, it's automatically a 10. Not that it matters, but. All right, so let's get into some that do more. So let's do log base 6 of 5x cubed divided by y. So we'll start out kind of taking baby steps with this, and some of you may pick up on it quicker and be able to do more than one step at a time, and I'm absolutely okay with that. But if we'll do it one step at a time, I think you'll see all the properties happening here, and it makes it easy. So what's the big thing that this log has? That big division problem in there. So I'm going to undo that first with what? Quotient property, which turns it into subtraction, right? So I've got log base 6 of 5x cubed minus log base 6 of y. Okay. Numerator is always first. Top part of the fraction is always first. Bottom part of the fraction is always what's subtracted. Now, will either of those two pieces break apart further? The 5x cubed has what in it? It's got an exponent. What's the exponent on? The x, not the 5, right? And then what's going on between 5 and x cubed? They're multiplying. So I'm going to get the 5 and the x cubed apart first using what property? Power, or not power. Product, because the 5, it's 5 times x cubed there. So I'm going to make that log base 6 of 5 plus log base 6 of x to the third. And then the log base 6 of y, there's nothing else happening with the y stuff, so I'm just going to copy it down. Yeah, everything's the same there. And then one more thing can happen here. That 3 can drop down with power property to the front of that piece. And there we have log base 5, or log base 6 of 5 plus 3 log base 6 of x minus log base 6 y. And that's our fully expanded form for that. Yes, ma'am.
So can you take the 3 out before you like take the 5 and X apart? Or is that
As long as the 3's only in front of the part that has the x. I'm fine with you doing more than one step at a time. I actually encourage that because it's going to save you a lot of time in writing if you do. So yeah, I would have probably done the blue step and the green step, as one step.
So if it was like 5x and then the 3 was on the outside.
Then you would pull that 3 out to the front, and then you'd have parentheses out there. Let's look at one. We'll get one that does that. Let's make one that does that, like Jaden's talking about there. UV. So let's say we had log base 2 of y to the 5th over 4x in parentheses squared, something like that. So this kind of encapsulates everything that we've talked about there, and then what Jaden was asking about too. All right, so what's the big thing that's happening here? Division. So I'm going to start out with breaking that apart with division. And then can the first piece, the y to the 5th part, can it be simplified any further or expanded any further? Yeah, the power thing could pull the 5 to the front. What about the next piece? Okay, so which one comes first? The power or the product? The power, right? Because the order of operations, what happens first? Power, right? Exponents happen first. So I can really pull this 2 out to the front, and then I've got log base 2 of 4x. So it's 2 times the log base 2 of 4x, and then I've got to expand the 4x part. So the next line would have 5 log base 2 of y. And then here's where it gets a little trickier, because it's 2 times that entire log. So when I break that apart, I've got to have the 2 on the log base 2 of 4 and a 2 on the log base 2 of x. Why did I put a minus 2 in front of that? Where did it come from? From the original problem, right? All of this stuff that has a minus sign was in the what of the original problem? The bottom part, the denominator, right? So anything that's in the denominator, it's got to have a minus sign in front of it. Anything that's in the numerator is going to be a positive in front of it. That's going to help us when we go to do the condensing here in just a second out of that. But keep that in mind. Anything in the denominator has got to have a minus sign in front of it. Anything in the numerator is going to have a positive sign in front of it, or a plus sign. Okay. All right. Let's get a natural log in there and throw a radical in there. Natural log of 10x to the 4th cubed root of y. All right, so cubed root of y, we got to talk about it for a second because we haven't done rational exponents yet. So cubed root is the same thing as the 1/3 power. That's whatever the root is, that's the denominator of the fraction if you rewrite it as an exponent. Okay, so cubed root's 1/3 power, 4th root would be 1/4 power, square root would be half power. Yeah, that's exactly right. So that idea, really easy concept. We don't have to have did the unit on rational exponents to have been able to do that. So easy thing. Now let's expand this dude out. So let's try to do more than one step at a time. So we got natural log of what? What's going on between everybody? They're all multiplying together. So I've got 10 plus what? X to the fourth, right? So that's going to be what can happen with that? Yeah, I can pull the 4 out to the front and then do natural log of X. And then the cubed root of Y, we just talked about it's the same thing as Y to the 1/3 power. So that would be 1/3 natural log of Y. And we did it all in one step. What's wrong with it? Gravity is against me. All right. That's okay. I don't know why I'm using alphabet today anyway. Because I use numbers. Yeah. 26. All right, so expanding using those properties. Let's go the other direction, which is the actually the more useful thing when we go to do solving is the condensing or writing as a single logarithm. So, indeed. Well, just think about what we were doing before was backwards, so that makes this the fourth, right? So the idea is you're finished when you have one single logarithm left. Okay, that's how you know you're done. So log base 2 of x plus log base 2 of y plus 5 log base 2 of w. Okay, so what are all of them doing? So that means it's going to turn into multiplication. No division involved because there's no minus signs. Okay, so when I put the first two together, that's going to be x times y. And then what's the last one going to be? W to the fifth. So it's going to be log base 2 of x, y, w to the fifth. All of them multiplied together. They're all added, so they're all multiplied together. All right, so this one has some pluses and some minuses. So minus signs indicate what? Division. And anything, just said it just a few seconds ago, or about less than a minute ago. If it's got a minus sign in it, it came from what part of the fraction? The denominator. So we know these two pieces are going to go into the denominator. Okay. These two pieces are both positive. So they're going to go where? Numerator. They're adding together here, so that's going to end up being what? In the numerator. Okay. Log base 7. Not in Algebra 2 you won't. The log base should be the same all throughout. Else you can't condense it into one. Over what? 5. All of that inside of one log base 7. You only need one of those. So we see the minus sign, putting stuff in the denominator. Positive signs put stuff in the numerator. Well, let's change stuff. Yeah. All right. Throw a little curveball into this one. Natural log really is just log base e, so it really doesn't change the rules any. Just changes what we got to write. Alien. So what goes to the numerator? What goes to the denominator?
4x on the numerator.
Okay, so I got a 4x.
What about the other one?
Oh, the last piece is positive as well, right? So it's positive, so it's going to go where? The numerator. So we're going to have natural log 4x to the 5th, w to the 4th, and then the only minus part is that y. So that condenses it down into that. Your grandmother what? We can. It's alpha. All right, so throw some parentheses in there. All right. So what does the parentheses do to things?
You gotta do it first.
What was that, Harv? It's like distributed property.
Negative.
So it makes both of those negative, right? So it's the same thing as having this as minus ln y minus 4 ln w. Yeah, it's okay. We're about done. So we'll save a little power. So now maybe we understand that that's happening. So that gives us a little definition into what goes up top and what goes in the bottom. 4x to the 5th on top. The bottom, yw to the 4th. That's it. Again, positive things go to the top. Things with a minus sign go to the bottom. When you're condensing, if you'll remember that, that's going to get you in the right direction pretty well every time. Last one. That's beta.
That's weird. Wait, did you say they did Greek?
That's Greek letters, yeah.
Did you take Greek?
No, I took math.
Ah.
That is a Z in the last parentheses there. They're all up in the math.
Oh, okay. Here we
All right, so I heard somebody say there's only one thing in the bottom, and that comes from where? Try again. That thing right there is the only part in the bottom. Now, everything else goes in the numerator, right? So that's going to be what? C to the 3rd. Now, let's do a little bit of rational exponent stuff here. 2/3 power The denominator's a 3, so that could be rewritten in a what root? Cubed root of y squared. Recognize both. If it's a short answer, I'll take either, but the denominator, just a y to the 1/3 is a cubed root of y. But anything, the denominator is the root that you're dealing with. So if it's a 2/3, the denominator is 3, and the numerator is the exponent on the variable, is what that works there.
So which one would you take?
On a short answer, I'd take either, but be able to recognize that it's the same thing if it's multiple choice. It may be either way.